The real shift this week is not that models got smarter, it's that the bottleneck moved to how we make them faster, more reliable, and more useful inside production systems. On one side, speculative decoding is starting to behave less like a blunt speed hack and more like a carefully engineered inference pipeline. On the other, LLMs are being pushed deeper into compiler optimization, where one good pass can unlock speedups across entire workloads. What connects all of this is a simple pressure test. Can AI systems deliver measurable gains without losing correctness? Let's explore the first paper, Domino Decoupling Causal Modeling from Autoregressive Drafting in Speculative Decoding. Domino, from Epic Lab at Shanghai Jiao Tong University and Huawei collaborators, tackles a core bottleneck in speculative decoding for large language models such as Qwen 3.4b and Qwen 3.8b. Autoregressive drafters like Eagle 3 preserve causal token dependencies but pay a sequential cost, while fully parallel drafters like dflash cut latency but weaken intra-block dependency modeling. Domino decouples these two goals by using a parallel draft backbone to generate block-level preliminary distributions in one pass, then adding a lightweight causal correction branch with a GRU-based encoder and a low-rank logit spacehead to inject prefix information without rerunning a full LM head. The training recipe is equally novel. A teacher-forced causal encoder avoids noisy, self-generated prefixes, and a base-anchored curriculum first optimizes the parallel backbone before gradually shifting weight to the corrected final logits. On math, code, and chat benchmarks including GSM, 8K, Math, 500, AIM25, Human Eval, MBPP, Live Code Bench, MT Bench, and Alpaca, Domino improves average acceptance length and speed up over representative baselines. On Qwen 3.8b, it reaches 5.49 times average end-to-end speedup under the transformer's backend and up to 5.8 times throughput speedup in SG-Lang, with a standout 7.92 times speedup on GSM, 8K versus 5.21 times for dflash. Ablations show the Domino head alone raises average acceptance length from 3.49 to 4.19 and speedup from 2.84 times to 3.31 times, confirming that lightweight causal correction is the key mechanism. Let's explore the second paper, Draft OPD on Policy Distillation for Speculative Draft Models. Draft OPD, from Shanghai Jiao Tong University and Shanghai AI Laboratory, tackles a bottleneck in speculative decoding. Draft models, such as Eagle, 3, and dflash, are usually trained with offline supervised fine-tuning on target-generated trajectories, but acceptance length plateaus because inference depends on draft-induced states, not static teacher data. The paper proposes on-policy distillation for draft models by combining target-assisted rollouts with error position replay. The target model first produces a stable speculative rollout. Anchors are recorded at each drafted block, and then the system replays drafting from those anchors so the target can score both accepted and rejected draft tokens at the exact failure states. Draft OPD adds an acceptance-aware objective that uses forward KL on accepted tokens and reverse KL on rejected tokens with exponentially decayed weights on later rejected positions to emphasize the earliest error in a block. Experiments on Qwen 3, 4b, Qwen 3, 8b, and Qwen 3, 30b, A3b. Thinking 2507 across GSM, 8K, Math, 500, AMI, MBPP, Human Eval, SWAE Bench Lite, and MT Bench show consistent gains over Eagle, 3, and dflash under matched flops. Average speedup rises to 4.86 times on thinking mode models and 5.31 times without thinking, with average acceptance lengths up to 6.6 tokens in non-thinking settings. On SG-Lang with FA3, Draft OPD improves throughput by 6% to 17% depending on model and task, confirming that verification time error replay translates into real serving gains. Let's explore the third paper, PassNet Scaling Large Language Models for Graph Compiler Pass Generation. PassNet, from Baidu, reframes LLM-assisted compiler optimization away from standalone GPU kernel synthesis and toward graph compiler pass generation, where the model must emit structured rewrites that plug directly into tensor compilers such as Torch Inductor, TVM, XLA, and MLIR-based stacks. The paper profiles 9,526 real subgraphs and finds a long-tail optimization ceiling. 43% of workloads slow down end-to-end under Torch Inductor's default pipeline, even though individual long-tail cases can see up to 3 times speedup. To attack this, PassNet dataset collects 18,086 deduplicated computational graphs from 100K PyTorch and PaddlePaddle models and expands them into about 279K training subgraphs using recursive folding for recurring, motif, prefix analysis for fusible intervals, and shape D-type generalization. For evaluation, PassBench curates 200 long-tail tasks with 2,060 subgraph-level tests and introduces error-aware speedup score, or E-state, which jointly measures correctness, compilation stability, and runtime speedup while resisting benchmark gaming via AST inspection, runtime dispatch, interception, and reverse evaluation order. Across frontier and open source models including GPT, 5, 4, Claude, Opus, 4, 6, Claude, Sonnet, 4, 6, GLM, 5, 1, Minimax, M2, 7, and Quindry, the best aggregate score still trails Torch Inductor by 37%, despite some passes achieving 3.02 times speedup on MaskFormer and 2.9 times on BGE ReRanker, fine-tuning Quin330BA3B on just 3,899. PassNet trajectories lifts AS from 0.139 to 0.371, a 2.67 times gain, showing the bottleneck is consistency and training data, not raw capability. That's a wrap on today's AI paper highlights. Thanks for watching.